When you speak in a busy room, you are blasting the air around you with chaotic, overlapping sound waves, vibrating violently as they travel outward. Your human brain naturally filters that noisy environment so you can understand the person next to you. But a computer doesn't have an intuitive ear. If you feed it audio, it just detects a meaningless, dense wall of raw physical frequencies. Before a digital assistant like Siri can process the meaning of your question, it has to solve a massive physics problem first. The linguistic hurdles are enormous. We don't speak in neat words. We slur and blend our phrases together. We change our speed and we speak over background noise without leaving clear boundaries between our sentences. To bypass this mess, engineers designed systems that hunt for microscopic phonetic patterns hidden inside the noise. Rather than waiting for whole perfect words, the software operates as a decoder, turning chaotic physical ambiguity into a precise, structured digital logic. Because raw analog waves cannot be analyzed directly by text engines, the software kicks off the translation pipeline with feature extraction. When your microphone captures an analog wave, the system immediately filters it, stripping background hums and room echo to isolate primary vocal frequencies. This chart shows the process of taking a one-dimensional analog waveform and then expanding it into a glowing spectrogram, a dynamic two-dimensional visual map that plots audio frequencies over time. Now that the audio is a visual map, the system applies an acoustic model. Deep neural networks deploy a vertical scanner sweeping across the spectrogram, analyzing frequency data clusters. The network hunts for phonemes, foundational units of sound like sh, ah, or p. It works like a high-speed court stenographer. A court reporter doesn't type out full English words while someone else is speaking fast. They listen for core phonetic sounds and type shorthand symbols immediately, trusting they can reconstruct the words later by extracting these phonemes. First, the software converts the messy physics of a voice into a string of standardized digital symbols. But a string of phonetic shorthand symbols is not yet a readable English sentence. Phonemes are inherently ambiguous. If the acoustic model extracts the sounds for the word pear, it hits a wall. Identical sounds can have completely different meaning and spellings, depending on whether you mean a matching pair of shoes or the fruit you eat. To solve this spelling ambiguity, the digital system passes the phonetic data to the final step, the language model. This probability tree diagram illustrates how the language model evaluates context. By looking at the preceding words, like I need to buy the system mathematically determines that the correct spelling is PAIR at 99% probability. Modern transcription relies on this mathematical probability, scanning the surrounding context to force ambiguous phonetic sounds into logical context. Early versions of this technology required engineers to manually code the rules connecting these three distinct steps, moving from spectrogram to phoneme to word. Today, AI relies on end-to-end deep neural networks utilizing transformer-based architectures like OpenAI's Whisper. Because these models train on hundreds of thousands of hours of data, they bypass the separated pipeline entirely. They ingest raw audio and output text in a single unified step. This diagram shows the efficiency of that modern architecture. Raw audio enters a single transformer node, and clean text in multiple languages exits the other side. It navigates thick accents and technical jargon because it learned the context and the phoneme simultaneously. Looking at the entire process, speech recognition connects the physical movement of air to the mathematical logic of a processor. It captures the fleeting, chaotic reality of the physical world and transforms it into the precise, permanent, and actionable world of digital information.